Good afternoon, everyone. I'm Hao Huang, Assistant Professor of Social Sciences Department. Welcome to the Illinois Tech Social Sciences Great Problems, Great Minds seminar series. For today's seminar, you can submit questions during the webinar by typing in the chat box. We will open the floor to questions at the end of the webinar. Today's speaker is Professor Zhang. Dr. Zhang is an Empire Innovation Associate Professor in the Department of Environmental Health Sciences in the University at Auckland State University of New York. Dr. Zhang received a PhD degree in environmental health and a master degree in statistics at the University of Michigan, and a master degree and a bachelor degree in environmental engineering in Tsinghua University and the Southeastern University in China, respectively. Dr. Zhang's research explores emerging topics in urban environmental pollution at the interface among climate change, extreme weather events, air pollution, and health. His perspective is to apply multidisciplinary approaches to address the complex environmental health problems. His research interest focuses on characterizing climate-related exposures, reducing the human health impacts associated with disasters, and exploring the role of environmental stressors, air pollution, natural environment, built environment, and the social environment in relation to chronic diseases. His expertise includes explosion science, air quality, environmental and occupational epidemiology, GIS, statistics, and data science, specifically including exploring the human health impacts associated with more frequent extreme weather. The second is characterizing the sources and human health impacts of air pollution with a focus on the role of air pollution on chronic disease development. Third is to investigating the role of built and social environment in the development of chronic diseases. The fourth is investigating urban compactor development, smart growth, transportation, environmental pollution, and sustainability. The fifth is to applying GIS and data science approaches in epidemiological and intervention studies. His previous work includes developing the first exposure model to estimate long-term exposures to PM10 to 2.5 species in the US, developing a comprehensive framework to characterize exposures and the risks due to traffic congestion, developing lower methods to characterize climate-related exposures, and quantifying the health impacts attributable to extreme weather, such as heat, cold, flooding, and hurricane. His research project, funded by public and private funding sources such as American Heart Association, National Institute for Occupational Safety and Health, and National Cancer Institute, and has been published in major science, public health, and medical journals, resulting more than 75 peer-reviewed publications in top journals such as the Lancet Science of the Total Environment, in the International Journal of Environmental Research and Public Health, I'm very delightful to welcome Professor Zhang to give us a talk.
Oh, okay. Yeah. Thank you very much for a kind introduction. It's my pleasure to give a talk at IIT and to share my research with you today. Can you hear me clearly?
Yeah, we can hear you
Okay,
clearly.
great. Yeah. So actually, I really love Chicago. So I have been in Chicago many times, and also I have some studies related to Chicago. So today, I will be sharing some of the Chicago specific studies with you guys. Applying applying multidisciplinary research approach to address environmental health problem is what I enjoy doing. So fortunately, I have been involved in a number of projects in past 15 years, which are at the interface among climate change, health, air pollution, and sustainability. In today's talk, so I will start with heat waves first. So here's a general background. So as a result of changing climate, more and more frequent extreme weather events occur. So let's start from Chicago. So after several extreme cold hit Chicago in recent years, Chicago now have the popular name Chiberia. So in some weeks of winter, Chicago was even colder than Antarctic. So look at this picture. So this picture shows how hot water turned into snow immediately. So look at this one. So this one shows the railroad tracks need to be unfair to keep trains moving. So Chicago is not only affected by the extreme cold, but also by heat waves. The typical example is 1995 Chicago heat wave. So this heat wave is short but intense. It lasts about 5 days. It caused about 700 deaths in Chicago area. So most of them are elderly and poor people living in the urban areas of Chicago. So look at this, the bottom picture here. So this figure shows the daily high and daily mean temperature and the daily low temperature during the Chicago heat wave. So here you can see, the highest daily maximum temperature is about 104 degree Fahrenheit. So this sets, a all-time high temperature in Chicago. So the Chicago heat wave, it is a milestone event. So after this event, so there are about hundreds of studies in the U.S. And worldwide to study how extreme heat affects human health. So many studies have found extreme heat is associated with increased risk of mortality and morbidity, including numerous endpoints, for example, heat stroke, hospital admissions, cardiovascular disease, respiratory diseases, kidney diseases, the birth defects. So meanwhile, so a lot of climate models project, more and more frequent extreme weather events in the future. So the Chicago heat wave also inspired me to study the 2011 Texas heat wave. So the 2011 the heat wave mainly affects Texas and the surrounding states, for example, Oklahoma, Arkansas, and Louisiana. So this slide shows some of the record-breaking facts. during the 2011 Texas heat wave. So the average temperature during the 2011 heat wave was 88 degrees Fahrenheit. So the average daily maximum temperature during the heat wave period was 99 degrees Fahrenheit. This heat wave also set the all-time highest temperature in Houston, which is 109 degrees Fahrenheit. So if we look at this one, Chicago one, so the highest daily maximum temperature is 104 degrees Fahrenheit. So here's 109 degrees Fahrenheit. So in the August 2011, 30 out of 31 days have the daily max temperature above 100 degrees Fahrenheit. So for the entire month of August, so National Weather Service issued heat advisories for 29 days. So here, if we just look at those, the temperature metrics. So the Texas heat wave is hotter than the 1995 Chicago heat wave. So at that time, one natural question in my mind is, what's the health impact of 2011 heat wave in Texas? So that's why, so this is the motivation for my study to look at the health impact of 2011 Texas heat wave. So basically, we conduct study to look at how heat wave affects mortality and emergency department visits in Houston. So here, here's the Texas. So here, look at this one. Here's, the Harris County, where the city of Houston is located. So here's the city of Houston. The city of Houston is next to the Gulf Coast. So our study period is the summertime from 2007 to 2011. So basically, we choose the multiple years in our study. We're using the years from 2007 to 2010 as the reference period. So we obtained the mortality date from the Texas Department of State Health Service. We use all-cause mortality after excluding the external causes. So what does this mean? So basically, we exclude those injuries, poisonings from the mortality. We also obtained emergency department visit date from one of my colleagues. We downloaded the weather date from the National Climatic Data Center. We also download air pollution data from the TCQ, which is Texas EPA. Although there are many studies on heat wave, we don't have the unified heat wave definition. So I will talk about this later in details. So how hot is too hot? So basically, we use a bunch of definitions to define the 2011 Texas heat wave. The first, we use the heat advisories issued by the National Weather Service, which is from the August 2nd to 30th in 2011. So we also use a few percentile-based definitions. So we define the heat wave as a period of 2 or more consecutive days with daily mean temperature above 95th percentile or 97th percentile or 99th percentile of daily mean temperature distribution in 2011. So why we are using the percentile-based definitions? Because how hot is too hot? different people, especially in different region, have different answers. So the people in the south, they have the relative high tolerance and or acclimatization to the temperature. So that's why we usually use, the local specific percentile-based definitions. So here's our statistical model. So basically, we are using the Poisson regression model. So we model the daily counts of mortality or ED visits as a function of the heat wave. At the same time, we also adjust for a few confounders. So look at here. Y is the daily count of deaths or ED visits. T means, the on day T. So basically, this is the time series. We have, we have the time series over the 5 summertime from 2007 to 2011. So DOW is the day of week. This is just a year number. This day of year. We use these variables to adjust for the unmeasured confounders that are associated with day of week and day of year. Now let's look at this one. So this is the binary variable for the heat wave days. For one day, if it falls in the heat wave period, we will assign 1 to that day. If not, we will assign 0 for that day. So look at here. We also consider the lag effect. So what does this mean? This means, someone go to hospital because, the exposure to high temperature at same day. Someone may go to hospital due to high temperature yesterday. Someone may go to hospital due to a high temperature due to the day before yesterday. So there's the delay effect, the lag effect. So that's why we use, the distributed lag nonlinear model here. So this slide shows this summary. So basically, look at this column. This, basically for the 2011 heat wave period. Here we just show the few key metrics. So here's the reference period. So basically, they are the same period during in the previous years. So if we compare the 2011 heat wave period to the reference period, here we can, for example, let's see, daily mean temperature. So comparing the heat wave period to the reference period, the average daily mean temperature increased by about 2.5 degrees Celsius. So if you look at the average daily max temperature, so the difference between the heat wave period and the reference period is about 4 degrees Celsius. So here, for the mortality, so there only so there's no major difference between the heat wave period and the reference period. However, here for the ED visit, we can see, a significant difference around, the 300 case per day between the heat wave period and the reference period. Okay, so here we show the results for mortality and ED visit. So this is results for mortality. These are results for ED visit. So let's look at this one. So for the x-axis, we have results for different age group for the entire population. Then we have, for the population less than 6 years old, between 6 and 65 years old, and elderly. Here we have different color. Different color represents the results for different heat wave definitions. So those one, are point estimate. So the vertical bar are 95% confidence intervals. So now let's look at the y-axis. Oops. So the y-axis means the excess risk, the percentage excess risk by comparing the heat wave days to reference period. So let's look at this one. So this one means by comparing the Texas heat wave in 2011 to the reference period, so the chance of going to ED department increased by 4% for the entire population. So if we use, more strict definitions, heat wave definitions, you can see, this estimate increase. So the one major finding here is, so for the entire population, so those results are statistically significant, and those results are even stronger for elderly. For example, look at here. By comparing the heat wave to the reference period, the chance for the elderly going to the ED department increased by 8%. Those numbers are not big, but however, please keep this in mind because this is for the entire population. So now let's look at the results for mortality. Here we see, all results, look at those vertical bars here. So all results include 0. So basically, all these results are not statistically significant. Okay, here is just quick summary. So this the first study on the health impact of 2011 Texas heat wave. So here I think someone may be surprised here because if we just look at the temperature, the 2011 Texas heat wave is hotter than the 1995 Chicago heat wave. The Chicago heat wave caused about 700 deaths in Chicago. But here, why we don't see significant results for mortality? So why is that? So the one major reason is that, so in Houston, the prevalence of air conditioning is about 97%. So basically, almost every home, every house have the air conditioning. So which is very different from Chicago, because for Chicago, from the Midwest, the summer usually is not that hot. It usually cool, only hot for about 2 weeks. So that's why a lot of homes, apartments don't have the air conditioning. So that's why when the heat wave hits the Midwest, like the Chicago, Michigan, because people in general, especially elderly, they are less prepared for the heat wave. So that's why you usually cause a large health impact. Okay, so now then because the summer is always hot in the southern US. So this study also motivate me to start a very vulnerable population, farm workers. I think all of us enjoy fresh vegetable and fruits every day. The question is, what do we know about this population? What do we know about farm workers? So we can think about the scenario, in the hot summer, the temperature is very high. Those guys, have to work very, very hard to harvest, fruits or vegetable. So more importantly, those people have very, very low SES. So 8 out of 10, the migrant and seasonal farm workers live below federal poverty line. They are very poor. And 7 out of 10 adults do not have insurance. So basically, their physical exposure to the extreme heat plus the, the high intense physical activities in harvesting plus low SES make this population very vulnerable to extreme heat. So that's why I conducted another study to look at how extreme heat affects outdoor workers, especially the farm workers. So we follow the similar approach in this study, but use a different database. So because I don't have enough time, so I will skip some of the technical details. So basically, we want to look at whether excess clinic visit occurred in hot days compared to the normal days for this. For the migrant and seasonal farm workers. So we obtained electronic medical records from the hospital system. They do have information about the farm worker and also the type of farm work, migrant farm workers versus seasonal farm workers. So we conducted a similar study. Here I just want to show some of the results. So here are the results for the total patient. Here are results for the migrant farm workers. Here are results for the seasonal farm workers. So those points means the heat effect. So basically, for example, look at here. By comparing hot days to normal days, the chance of going to a clinic for the migrant farm workers increases by 80%. So look at here, the Houston study, the Texas cave study. For the general population, by comparing the heat wave to the reference period, the chance of going to ED department increased by 4%. Look at here, 80%. So this means, the heat is, poses a significant threat to this, the population. Then we stratify analysis by gender. So look at here. This is results for the male migrant farm workers. So look at here. This means, by comparing hot days to the normal days, the chance of going to a clinic for the male migrant farm workers increases by almost 100%. So we can see, this is a significant issue for the migrant farm workers. Here just is a quick wrap up for this study. So this is the first study to look at impact of heat on mobility in migrant and seasonal farm workers using the health record. Okay, so now let's go back to our fundamental question. So how hot is too hot? So this is, I mean, the fundamental question in temperature epidemiological studies. So how hot is too hot? So probably, if I ask, 100%, probably I'll get 100 different answers. So basically, our perception of heat depends on many factors, depends on many weather parameters, plus many physiological factors. So look at this picture. For example, here, look at here. So there are many weather parameters, temperature, apparent temperature. So what's the apparent temperature? So it's a function of temperature plus humidity. Dew point, relative humidity, absolute humidity, atmospheric pressure, wind. So we can think about, given the same temperature. So if you stand, next to Lake Michigan, or if you stand, in the city of Chicago, the center of Chicago, you probably have, different, the heat perception. So in the temperature epidemiological studies, we usually use, either temperature or both temperature and relative humidity. So usually, so this is because those weather parameters are usually highly correlated. So actually, we have done a few studies to look at to address this question. So here I just want to list one example because most weather parameters are highly correlated. So the one interesting question is to look at which parameter is most important in predicting mortality, heat-related mortality. So we use, a machine learning method called random forest. So basically, we rank all, all the weather variables. So here, if you look at, the y-axis, this shows, a number of weather parameters at different days. Axis, this means, this basically is an importance score. So higher value means, they are more important in predicting the outcome. Here we can look at, the top 5 ranked, weather parameters. The first one is, daily mean temperature. 2 days ago. So actually, those are results, specific for Chicago. We're using the mortality in Chicago. So our paper look at a few cities. Chicago is one of those cities. The second one is the daily mean apparent temperature at the same day. So this one is daily mean at apparent temperature. This is the daily mean dew point temperature 2 days ago. Or look at here, daily mean absolute humidity 2 days ago. Okay, So now let's move to air pollution part. So I want to talk about a few examples about air pollution exposure assessment. So in epidemiological studies, we usually have the 2 key components. One is about exposure, another one is the diseases. So the idea is to link exposure level to disease status. So those work are mainly to provide a better exposure estimate for individuals. So let's look at the first one. So there are many studies on the PM10 or PM25. So both PM10 or PM25 are criteria pollutants regulated by US EPA. So PM10 are particles in air with a median diameter less than 10 micrometer. So PM25, so-called fine particles with a median diameter less than 2.5 micrometer. So we really know very little about chronic health effects of PM10 to 2.5. So why is that? The first one, because PM 10 to 2.5 is not a critical pollutant. So we don't have enough monitors to monitor the cause particle. So for example, like Chicago only have one or two monitors that measures the PM10 to 2.5. So for the IP studies, ideally want to predict exposure for every individual. Then we link individual level exposure to individual level disease status. So look at this map. For example, in this city, this is just a hypothetical city. So, for the PM cause particles, there are usually only one or two monitors in major cities. So if we use, the concentrations monitored at this measured at this monitor for the entire population in this within this city, that will cause a lot of exposure misclassification. Okay. This project is being collaborated with the MESA study. So MESA study refers the multi-ethnic study of atherosclerosis. So this means a very large cohort study, follow 6,000 participants in 6 cities. Chicago is one of them. So this project is called the MESA cause particle project. Is funded to add the detailed characterization of the cause particles PM10 to 2.5 and to look at how the cause particles affects cardiovascular diseases and respiratory diseases. So we in this study we collected the PM10 and the PM25 samples at 70 locations for each city. Here I want to emphasize one point. So actually we collected simultaneous samples at 35 locations for one season. The 70 locations for 2 seasons, winter and summer. So we collected the samples over a 2-week period in both summer and winter to account for seasonality. After we collect those samples, we analyze the mass concentration and also the chemical species. So for our exposure modeling, so our goal is to predict individual level exposure to the PM10 to 2.5. So basically, if you tell me any address of a participant, I will use our model to predict exposure at that location based on our model and also a number of the covariates. So for our model, we choose the mass concentration and 4 selected species: copper and zinc, which are indicators of the brake and tire wear in all cities. Silicon and phosphorus are indicators of soil and agriculture. So we tried, the two type of models, land use regression and universal kriging. So what's land use regression? So basically, land use regression is an extension of linear regression. It just uses a lot of GIS-derived land use variables. So universal kriging is an extension of the multivariate linear regression, but account for the spatial correlation using the semi-variogram. We built our models for each season, and also we built models for each city and cross cities. So finally, we use cross validation to evaluate our models. Okay. So here, this slide shows, the variables used in our study. So here we use, the variables in those categories: land use, transportation, population density, emissions, NDVI. So, for each category, we also create a lot of buffer variables around each participant address. So finally, we have over 600 variables. However, for our observation, we only have about 35 observations per season, 70 observations per city. So this is a high dimension question. So the first, we screen some variables based on their spatial variation. Then we use a machine learning method called lasso to further reduce number of variables to the 15. So lasso is the very popular and breakthrough the machine learning method 15 years ago. So a few papers, a few lasso papers got citation more than 20,000, 30,000. So finally, we conducted exhaustive search to examine all possible combination of covariates. Okay, here I just want to show some of the results. So here we have results for land use regression and universal kriging. So if you look at here, so basically results between land use regression and universal kriging are similar. Look at here, 0.68, 0.68, almost the same. So here means, universal kriging doesn't increase the model performance because we already use a lot of spatially correlated variables. Here we also see here, the model performance vary by cities. We have the best performance in Chicago. So this is mainly because we have the larger spatial variation in our samples, in our observations. So the model performance also varies by the species. So here, so the model performance for all cities are not very good. So why is that? So our initial thought is to build a universal model across all cities. So if it is successful, we can apply this model to our city. But unfortunately, the model performance is not great. Why is that? If you want to build a model across cities, the model will pick, the features, the geographic features that exist in all cities. For example, in Chicago, distance to Lake Michigan may be a very important feature. But however, if you use, models data from all cities, this feature will not be selected because other two cities don't have this feature. Here just our final product. The background is our prediction maps. So basically, for every grid cell, we're using our model to make the prediction. Then we draw this prediction maps. Here you can see a lot of small dots. So one dot means a MESA participant. Here you see those the squares, diamonds. Those are sampling locations. So this study is great, but however, because we collected the samples simultaneously at 75 locations per season. So this study, the drawback is very expensive because you have to have a lot of instruments to measure pollutant concentrations at the same time, and also requires a lot of maintenance work, logistic work. So that's why we moved to another approach. So nowadays, there are a lot of satellites orbiting around Earth. Look here, we have the thousands of satellites. So those satellites collect many parameters. One parameter is called AOD, aerosol optical depth. So AOD is a measure of scattering and absorption of light by particles through a vertical column of the air in atmosphere. So AOD is proportional to the PM concentrations. So using the satellite data, we can have a very good spatial coverage. For example, we can have a spatial coverage over a large region and entire US and entire world. They also have the very good temporal coverage. Usually we can get the daily information from satellite. So we extend the approach in this work. Basically, we include AOD from satellite into our models. I will skip the details. I just want to show some of the results. So here's our AOD models for Texas. So here our final prediction map. We also have done AOD models in China, in Beijing, China. So this work, was selected by Environmental Science and Technology as a feature article in 2015. So now I'd like to talk about a few very exciting ongoing projects. I think everyone uses Google Map, right? When we use Google Map, sometimes we look at Google Street View peak images. So look at this car. So this is a Google Street View cars. They drive through a lot of a lot of places in the city to take the pictures. So we install some of the air pollution instruments in the Google Street View cars. So when the Google cars take picture, they also take the measurement of air pollutants. Here is just one example. Because the Google Street View cars made a lot of stops in the city Houston. So we know their location. We also have the measurement at those locations. So now we are using the machine learning technique to build a very fancy prediction model for PM, nitrogen dioxide, black carbon in Houston. Here, I just want to show you some of the pictures. So here's a model prediction for PM 2.5 in Houston. Here's a prediction map for nitrogen dioxide in Houston. Okay, so finally, I want to talk a little bit about a new concept: total environment and urban exposure. So traditionally, when we look at the health effect of pollutants, we will look at a few pollutants at one time. In reality, we know we are exposed to multiple environmental factors simultaneously. So look at this diagram. So the total environment or urban exposure basically is a combination of natural environment, green space, park, air pollution, built environment, and social environment. So all those environmental factors plus genetics plus lifestyle, smoking, alcohol, drug use, physical activity. So all those factors play together and they lead to the health effect. So now we're working on the project called Cardiac Urban Exposure Study. So basically, we look at 4 cities in this core study. So this core study includes 4 cities: still Chicago, Birmingham, Oakland, and Minneapolis. So this map just should give you an idea about area deprivation index. So basically, those red, yellow colors means most disadvantaged areas. Those blue, dark blue, and light blue means least disadvantaged areas. So here we have 1,000 variables, but here we only show the correlation matrix for about 30 variables. For example, here distance to the actually this is results for Chicago. For Chicago, here distance to the Lake Michigan, green space, PM, species, neighborhood deprivation index, and also many other variables. Okay, now finally, I want to thank all my mentors, collaborators, students, and the funding sources. I'll stop here. So, any questions?
I think Dr. Zhang gave a very interesting answer and also very cutting-edge technologies introduction about the current air pollution and also the extreme weather, such as the heat, how will actually affect the people's health. So currently we open to the questions. So I think I can ask a question first. I think you mentioned at the end, for different factors, factors actually influence the health impacts, inherent characteristics and also policy programs and also lifestyle and the different environment factors. So how do you see these different factors for their different extent or different significant for people's health impacts? So and which one is more important, or actually they are all important? And also, I think you mentioned more about built environment here, and how actually the policies will affect the health impacts, especially for your research, it seems your research is a long-term research.
Thanks, Dr. Huang. Yeah, both are great questions. I mean, for first one, actually, because we have so many factors, many environmental factors, genetics plus, I mean, lifestyle factors. So which one are more important? So that's why that's I mean, what we are trying to do. For example, because one technical issue that a lot of factors are correlated. So that's why that's something we are trying to do. Yeah, and also this this question is more than it beyond just one study. So we need multiple study to answer this question. For example, individual level factors, neighborhood level factors. Which factor contribute more to certain diseases.
So, which means that you look at different spatial scales also, and
Yeah. So basically, I mean, we try to, I mean, combine individual level factors with neighborhood level factors. But we don't have the unified definition of neighborhood. So that's why for some studies, we use a lot of buffers. For example, which buffer is the best is the best.
yeah, that's kind of actually when we do the research. So how to decide like a threshold? Sometimes it's kind of hard questions.
Yeah. I think that's we don't have the best answer to this question. Usually, I think it really depends on research question. For example, for the physical activity, usually I think a lot of studies using like the 1 mile, something 1 mile, 2 mile as a cut-off point because they feel the 1 mile or maybe 2 miles are reasonable for people to walk. But still, this I mean, there's no I mean the unified answer. So usually, I think I mean it, it's good it's good to try some the sensitivity analysis to look at different buffer, different thresholds.
So and
So,
also
how do you get people to want to address these problems? I mean, it's one thing to identify them, but how do you make people want to fix them?
Uh, okay, so I think this is a great question. I think one thing is, I mean, to identify the major risk factor, a contributor. Then, for genetics, at this right now, there's, I mean, we cannot change our DNA, very hard, challenging, right? So, for risk factors, some risk factors are modifiable. For example, air pollution, maybe physical activity. So, for example, if I'm in the city government uh, builds more green space, more small parks, create more the bike route. This may increase the physical activity. And also, for some the lifestyle behaviors, smoking, alcohol, we may try some intervention or prevention, to reduce like the smoking and alcohol. So basically, I'm trying to say, we don't have the simple solution for a lot of diseases.
Yeah, and unfortunately, people don't even like simple solutions, so I don't even know what to do anyway. I mean, it almost feels hopeless at some level. But I just okay. Thank you very much.
Yeah,
but
thank you, Jeff. Yeah. Actually, for a lot of diseases, we don't fully understand the biological mechanism. And also, for a lot of chronic diseases, we don't have the treatment. For example, like the diabetes. Once the people get diabetes, we don't have the, some of the magical surgery to make those people from diabetes to the normal, status.
Yeah, I
that's why,
agree.
yeah.
It's a difficult problem. I just wish I knew how to solve it.
Yeah, I think that should be ideal. I also have the engineering background. For us, we just want to solve the problem.
So just to follow these questions, so do you think actually when we solve these problems could be like variance by the locations? Or is it just now you mentioned like for the taxes and for the Chicago, even both have the heat, but Chicago has more people died from this from the heat than the taxes. So it's because actually since the Texas people live there, their climate or their temperature, they are more. Besides, you mentioned like air condition, it's possible they are more like get used to that kind of temperature, and also in the opposite example is like when the Texas they hit by the extremely cold, then they have the higher mortality seems so it's so which means do we need to deal with these kind of issues by locations?
Yeah. I think this, the fantastic point. So actually, after, the 2011 Texas heat wave study, so one of my doctoral students work on her dissertation, focusing on the cold weather in Texas. So I can give you guys one example. So, for example, you guys live in Chicago, right? Sometimes we still, drive during the snow. But in Houston, in Texas, Houston, so we usually have the snow every few years, a little snow, very light snow. So once, we have the light snow in Houston, the entire city will be shut down. So all school will be closed. Almost all agencies will be closed because the people, here less prepared for the cold weather. But this is very normal in the Middle West. When I live in Michigan, sometimes I have to drive, you know, during the snow. Snow for me, is not surprise. But here, I mean, so that's why the local culture preparation, a lot of factors, play a role.
I see.
Mm.
So which means the how actually and the policies is also and the policies to help persons responsible to the this no matter is heat or cold is also important. So,
Yeah. So from the government agency perspective, the government, agency need to prepare well for disasters, extreme cold, the extreme hot, hot weather. For example, you can deliver like the warnings to the population, especially for the vulnerable population. You can have the cooling centers, in the hot summer for those vulnerable population. And also you can, maybe have more trees to reduce the urban heat island because urban heat island is very common in almost all cities in the US, in the world, in the world.
I see.
Mm.
So have any questions? Other questions? So seems no other further questions. So I think my last question is for your the first studies you look at how actually the heat impacts under mortality by age. So do you think have other social factors also affects these impacts?
Uh,
Because it seems the age is pretty significant, so the older people affected the most by these heat impacts.
The answer is yes, yeah. So for example, SES, low SES, for example, 1995 Chicago heat wave. So most of the deaths are poor people.
Okay, so which means
Yeah, so that's why, for my second study, the farmer workers, this population have a very, very low SES. So most people are poor. Most people do not have insurance.
I see. I
Mhm.
see.
So, I mean, if they are poor, usually, for example, they cannot afford air conditioning in their home or house, in their homes. Yeah.
Okay, I see. Even yeah, I think Colorado is also the place not not very hot for the temperature.
Mm-hmm. Yeah, yeah. So that's why, for the heat wave, usually heat wave have a large impact in the north of US compared to the south of US. But cold have a large impact in the south compared to the north.
I see.
Mm-hmm.
I see. Thank you so much. I think thank you very much for your great talk. So usually we give the applause to the
Yeah, thank you.
speakers at the end. Thank you.
Yeah, yeah. You are welcome. Yeah, thank you very much.
Thank you so much. Thank you.
Thank you.
Have